to help us understand stoichiometry, the first thing I want to do is relate it to a s'more. Okay? And I apologize, no, we aren't making s'mores today, but we will be making s'mores later on in this unit as part of the lab. So, and yes, of course, we'll eat them. I don't know why people ask that. Why would you make a s'more and not eat it, right? So, I understand that your equation for a s'more might be different, but for my analogy's purpose, I ask that you just accept this equation as the truth, okay? So my balanced equation to make a s'more is that I need 2 graham cracker halves, I need 1 marshmallow, I need 6 squares of chocolate, like so you know, like in a Hershey bar, how it breaks into like the teeny squares, 6 of those, okay? And in the result, I get 1 s'more, okay? My balanced chemical equation for making a s'more. So what we're doing today connect back to the problems we look at here with a s'more. So let's say, for example, with my s'more, what if I had, here's a simple one for starters. Let's say I had plenty of graham crackers, I have plenty of chocolate at my house, but at my house I only have 4 marshmallows. How many s'mores can I make according to this recipe?
4.
Why just 4?
Because each recipe requires 4 marshmallows.
Yeah, because the ratio of marshmallows to s'more is 1 to 1, right? So it limits how much I can make. That's all we're really doing today. We're just changing, and it's not talking about s'mores. It's going to talk about calcium oxide instead. But the idea of how a balanced chemical equation relates the ingredients and the products together is what stoichiometry is all about. So let's say, for example, if I have 24 squares of chocolate, and I want to make the max number of s'mores, okay? So I don't want any chocolate to go to waste. And we want to figure out how many graham crackers do I need to make that possible, okay? So in that box underneath there, write this out with me. And I know for some of you, you're going to moan and groan inside because we don't let it out in here, okay? Because I'm going to make you show your work, but I need to see it. Okay, come test time, you don't have to show it to me anymore. But today and next time, I need to see it because that's the only way I can help you if something isn't quite right. Okay, so I need you to write out all your work and all your units. Units are important because that's make it what it is. So just like we did with stoichiometry before, what I'm going to encourage you to do is to always start by underlining what it is that we know. And then we're going to circle what we're trying to find. First thing you have to do whenever you're trying to solve a problem is this. You have to know, well, what do I know about it? And where am I trying to get to in the end? Okay? The next thing we do is we take the thing that we've underlined, and that's the start of our conversion. So I have 24 squares of chocolate. I then set up my conversion factor. And from what we've learned in the past, how do I know what unit goes on the bottom?
The one you're trying to divide out.
Good. Whatever I'm trying to cancel. So since squares is here, that means squares of chocolate go on the bottom. And then how do I know what goes on top?
What you're trying to get.
Yeah, what we're trying to get to. So we're trying to get to graham crackers. All right, the question is now, how are graham crackers and squares of chocolate related?
They're not.
Mitchell? So from the balanced equation, we see that there is 6 squares of chocolate for every 2 graham crackers. Okay, this is going to be the new thing we learned today with conversions is using a balanced equation. That's why we had to learn how to balance first. So, Mitchell, you can have a smiley face for that, by the way. All right, you times that all through, and you should get 8 graham cracker halves is how many I need. Yeah,
So the main goal is to not have to convert to s'mores to find out the graham crackers, but instead to use its own equation.
Exactly. Yeah, that's the cool thing with stoichiometry is we don't, you can relate any 2 things together. You can relate a reactant to a reactant to a product to a reactant, because they're all connected. Yeah, came in.
Well, so it says 24 squares, so I just did, 6 times 4 equals 24, so I just times everything by 4, and then I got, would that still work?
Yeah, so in a sense, that's what we're doing here, right? Because you looked at the equation, right, and said, okay, well, it's originally 6, so now if it's 24, it's changed by a ratio of 4. Exactly, and that's really what's going on, is we're just, in a sense, if we were to change the balanced equation so that's a 24 instead, how do the other things change in result? The reason why I'm having us set it up like this for now is because on the assignment you're going to see we're still going to start getting decimals and things. So it won't be quite as straightforward of how much it's changing by, so that's where this will come in handy, is when you can't directly see the change. But your logic is totally sound. Okay, so once again, just as a review, when I use the term stoichiometry, right, fun little word that makes you feel super smart.
Wow.
Here's you are. It's really just talking about the relationships in a chemical equation. That's all stoichiometry is just comparing two things to one another. The way that stoichiometry works is it's based off the mole ratio. Okay, I have to know the mole ratio. I have to have a balanced equation because that's what connects our pieces together. Particularly when I talk about a mole ratio is talking about the coefficients in a balanced equation. And the coefficients are these big numbers out in front. The numbers we had to balance like we learned last time. Okay, so for example, in this problem, if I'm telling you 2 moles of Mg, from the balanced equation, that's going to be equal to 1 mole of O2. And notice that it's not the subscript, it's just the coefficient, which is also equal to 2 moles of MgO. So that is your molar ratio for this equation that compares them all to each other. It's a 2 to 1 to 2 ratio. Okay? All right, so let's try a problem here.
Does it matter whether or not they're on whatever side of those arrows?
Yeah, it doesn't really matter what side of the arrow they're on because they're still at equivalency. Okay, so let's say, for example, I ask the question, from this equation, if I have 5 moles of magnesium, and it's going to react with how many moles of oxygen? Right, so very similar equation actually to our s'mores, but now we're just talking about magnesium and oxygen, so a little less tasty of an equation. The idea is still the same, okay? So we always start with what we know. So I'm going to write down 5 moles, so write this in your box down there. So if I have 5 moles of magnesium, okay? Somebody by raise a hand, don't say it out loud, but can somebody tell me what's going to go on the bottom here in terms of a unit? What unit will go on the bottom for us? Amanda? Magnesium. Good, because I wanted to cancel out, right? And particularly mole of magnesium. Very good, have a smiley face for that. And then what unit will go on the top?
Moles of O2.
Good, whatever I'm trying to find. So in this case, it's moles of O2. Good, and you got a smiley face for that as well. All right, now everybody, don't say it out loud, but point with your finger, and there's a few places you can point that are all correct. Bless you. Point with your finger, where would I find the numbers to plug in here? Point with your finger where you're going to look to find those numbers. And don't point at your neighbor.
That's kind of easy.
Good, I think we're all mostly pointing the right way. You should either be pointing at this equation or the one that's on your paper. Okay? A mole to mole relationship comes from the balanced equation. That's the only place it comes from. So I look up there and it says for every 1 mole of oxygen, I have 2 moles of magnesium. So we have 2.5 moles of O2. Just like before when we did stoichiometry, recognize that this cancels, and the only thing that doesn't cancel is the thing that you've circled. Right? That's a big hint that you've at least set it up correctly. Questions on that one? All right, try this next one for me on your own. Ready, go.
That's so bad. Did you know that keeps coming up and we don't make all the money? My mind is up here.
Okay, all right, don't say anything out loud, everybody, but raise your hand if you can see my mistake I made up here on the board. Don't say anything out loud, just raise your hand if you know my mistake. Give me a second to compare yours to mine.
Oh. Oh, I know it.
Okay, keep your hand in the air if you don't mind sharing with the rest of the class. Okay? Alright, Jason, what did I do wrong here?
You switched the 3 and the 2.
So how do I know that the 3 should go on the bottom?
Because that's what it is in the equation.
Very good, right? Mole to mole always comes from the balanced equation. Okay, I want you guys to notice something that's going to help you a lot here as we start adding on more steps, okay? Everyone look up here at this. So notice that on top of the fraction, I have KClO3. On the bottom of the fraction, I have O2. The only time you can have two different elements or compounds on top of each other is when it's moles. If it's not moles, you can't relate them. You can't relate grams of one thing to grams of another. Or liters, you can't relate. The only thing we can relate is that mole because of the balanced equation. So as we start adding on more steps, be very cautious if you ever see that these are different and these are different, you're doing something wrong and you need to add another step in there. Okay, when in doubt, we're always going to go to moles first because that's what connects them to each other. Okay, questions on this one? In the end, you should have got 6 moles of KClO3. Recognize on your assignment tonight, if you don't put moles and you don't put KClO3 as well, it is incorrect. You need both of these units to signify what it is. Okay, on the next one, you should have gotten, in the end, 23.1. 23.1 moles of O2 is what we should have gotten. Everyone see or have a question on that one? Yeah.
For order, like, don't you do 18.5 times 5 and then divide by 4?
That's how I would normally do it. Yeah, as I times across the top and then divide the bottom. You could, like, times it as a fraction. As long as you follow, like, the right mathematical process, there are different ways of plugging it in.
So if you did 18.5 divided by 4 and then times it by 5, would you get the same answer?
Yeah, it should still work out. Yeah, it should. One thing as a side note, everybody, just a reminder with significant figures, the way you determine them is really just off the beginning, because these conversions are exact. So you don't have to look at those, but since this had 3 sig figs, that's why your answer should have 3 sig figs. So technically, if you didn't have 23.1, it's not all the way correct, based off those sig figs, which I will be looking for on that assignment, okay?
So it's always the...
Yep, whatever you first started with, however many this has, how many your answer gets. So. Okay, last thing we're going to do today, and then we'll give us time to work on our homework in class, is let's talk about this problem here. Okay? So there's something different. Oh, gotta say this. If you caught my mistake, you can give yourself a smiley face.
Mistake.
Okay, don't say it out loud, but let's earn another smiley face here. From you reading this question, do you see what is different about it from the 2 ones we did before? There's something, I mean, besides the equation and stuff, there's something else that is very different from the other ones we've done. So I'll give you a second to read that and see if you can catch on what's different about this problem from the 2 we just did. No, good reminder for that. Mitchell, what do you see?
It didn't give us the how much water in moles we're going to have to put.
Yes. We're starting with grams this time, not with moles, okay? So notice that I'm starting with 50 grams of water, and what is it I'm trying to find?
Moles.
Moles, right? So if you caught on and you saw that we were starting with grams, you can have another smiley face. Okay, I'm going to write something that's incorrect. This is good. This is where we start. But I'm going to write something that's incorrect to help us hopefully, I'll make the mistake for you so you don't make it again. Okay? Common mistake that we do. So grams of H2O goes on the bottom because I want it to cancel. And then normally I'd say, all right, well, I want to find moles of CO2, so I'd put that on top.
No, he's going to find moles.
Why is that? Why can't I do this in one step? What's wrong with that,
You
Nathan?
can't just directly convert from grams of water to grams to moles of CO2 because they aren't.
Yeah, this doesn't make any sense at all, right? This is like saying if I have 50 grams of donuts, how many chicken wings is that? Exactly, like, huh?
It's like weight, calories.
Like it just doesn't make, that was a really weird analogy, but that's what you're trying to do here. So, I don't remember who said it in the back. What do I have to go to first before I can go to moles of CO2?
Since it's a mole ratio, you have to
Moles of
convert to moles.
H2O. So we have to get to moles of the same thing in order to be able to relate them. All right, and where do I find, how do I do this conversion? This is going back. Look up at our roadmap if you forget. We're going to come back to that here in a second. To go from grams to moles, we use the molar mass, which some of you may remember is 18.02 for water. In every 1 mole, right, that's just added up from the periodic table.
Oh, so it's like, if we don't know the A, the add more.
Yes, you will have to add them up if we don't know it. Right, so this came from the periodic table though.
Oh,
My preferred method is just to keep going. You could solve it and get an answer and then go again. But I just like to keep going with it. So grams have canceled. So I had moles of H2O, and now I want to change it. So moles of H2O goes on the bottom. And now what will go on the top?
moles of
Yeah, now I can relate it to moles of CO2, because moles are always relatable. And where do I find that relationship?
in the equation.
Very good. In the balanced equation, so it's water, 4, 2, bless you. And then you plug it all in, right? So you could do it in, like some people like to plug it in as fractions. I like to just times, divide. However you want to do it, as long as you get the right answer, that's good. But I encourage you to try it right now, plugging it into your calculator, just so that if you have calculator problems, I can help you with them. Okay?
I got 2.0, is that
That is right. Yeah, don't. After sig figs, it's just 2.1.
right?
So water needs to be converted to a mole.
No way.
Did you get that too?
Yeah.
Oh, good.
Do I get this man?
Sure.
Does that mean
You
I
get 2.1, you can have snide.
Yeah.
That's why it's a curve.
Okay, last thing, just as kind of an overview. These are the basic steps whenever you do any sort of stoichiometry that you always want to take. Step 1 is you need to know what you're trying to find and what you're starting with, right? My plan is I like to underline that and circle, so focus back at front up here, everyone. Okay? After we know what we're trying to find and where we're trying to go, a key thing we need is you have to have a balanced equation. Right? There's no way to connect moles without it. So if for the problem it doesn't give you a balanced equation, you need to write that out yourself. Or like on today's assignment, I was nice and gave you the equations, but you might have to balance them on your own. Okay? So be careful as you're balancing them. Okay? And then finally we line up our different conversions and then times it all through. Right? Remember the rule with the conversions that they have to be equivalent to put them over top of each other. So I've made us a new roadmap that if it helps you, you can use. It's a little bit bigger than the last one, but I hope you see that it's actually just a mirror image of itself. Okay, so it's that same roadmap on the wall, but now we have 2 different situations because of converting from one thing to another. Bless you again. Okay, so grab a pencil and let's fill in this roadmap of how we get from one place to another. If I have moles of something and I want it to moles of something else, what do I have to use there? How do I get there? The mole ratio, which comes from that balanced equation. Okay, so fill this in on your roadmap with me here.
I've never seen that.
My sister had me.
Okay.
I forgot that's why I put them on.
Starting to come. Starting to come.
Often this right here, everyone, is known as the mole bridge. Because notice, it's the only way to get from this side to this side is you have to go through that mole ratio. That's why converting to moles should be normally your first thought if you're not already there. The rest of these pathways are what we've done before. Back in, I don't remember what unit it was, but in another unit, when we learned that roadmap the first time, these are all just repeats of it. But let's review really quick. If I have moles of something and I want to go from liters of something, what do I have to use to get there? Good, molarity. Okay, so molarity is the pathway to go from moles to liters or liters to moles.
What do we have to do to get from moles to liters for molarity?
It just depends on how if you flip it upside down or not, right?
Okay.
Because the liters is on the bottom or on top.
Is it just like same thing for grams?
Say that again.
Is it like the same thing for grams?
Yep, same thing. So because when we go to grams, it's the molar mass, but sometimes it'll be on top and sometimes it'll be on the bottom, just depending. Yep. What's the pathway to go from moles to particles? What do I use there? That big number, right? Avogadro's number? Avocado's number?
What's the number?
6.02 times 10 to the 23rd. So Avogadro's number is what gets us there. Okay. Moles to particles or particles to moles. Then, we did this one already, but moles to grams, what do I use for that? Molar mass. Good, so write that in up there. Molar mass is what gets us from grams to moles and moles to grams. Which molar mass just comes from the periodic table, adding it all up. And then finally, to go from moles to kilograms, that's the molality. Yep, so be careful with that one, it sounds similar. Molality. You could go 1, 2, 3. Right? Nowhere else to go. 1, 2, that just ends at 2. Anywhere else? The max you're going to do right now is 3-step processes. On today's assignment, it's only 1 and 2 steps actually. So if you do any 3 steps on today's, I'd rethink what you're doing. And then next time we'll spend more time practicing some of the 3-step ones.